Today we are going to discuss about the various types of organic reaction intermediates. First, let us consider a single step reaction. In a single step reaction, as the reaction progresses, the energy changes as shown in the graph. The energy of the reactant and the energy of the product are shown. In between that of the reactant and product, you find a maximum in energy which corresponds to what is known as transition state. The maximum in energy corresponds to transition state, and remember, the transition state cannot be detected by any methodology, and it cannot be isolated and characterized. And during the transition state, the bonds are being partially broken and partially formed, and it is a purely imaginary state because it cannot be isolated and characterized. This is the case of single step reaction. Next we come to a multi-step reaction. In a multi-step reaction, the energy progresses during the reaction as shown in the graph. You find the reactant and the energy corresponding to the product. This is for a two-step reaction. The energy changes during step 1 are indicated, and the energy changes during step 2 are indicated. And there are two maxima in the curve, and the two maxima correspond to the two transition states during the two steps. In between the two maxima, you find a minimum, and that minimum corresponds to that of the intermediate. What you find is that when you find two steps, you have one intermediate. The transition state cannot be detected, whereas the intermediate can be detected by instruments. The transition state cannot be isolated, whereas the intermediate can be isolated and characterized using different methods. Here we found that when we have two steps, we have one intermediate, that is the minimum between the two maxima. For two step you will have one intermediate, for three step you will have two intermediates, and for four steps you will have three intermediates, and so on. For n steps you will have n minus 1 intermediates. The transition state is real. The transition state is imaginary, whereas the intermediate is real because it can be isolated and characterized. It can be detected. Intermediate is real, whereas the transition state is imaginary. We'll now discuss the different types of organic intermediates. Here you find an example where you have the two carbons joined by a sigma bond. Now we find the two electrons constituting the covalent bond between carbon and carbon are shifted to one of the carbon atoms. This is heterolytic fission. The carbon on the right side will have two electrons, whereas the carbon on the left side will carry a positive charge, and the carbon containing the positive charge, you call it as carbocation or carbonium ion. The carbon on the right side carries the lone pair of electrons and it is known as carbanion, and it has a negative charge. The carbonium ion contains three bonds, three bond pairs, and so it is flat, trigonal planar, whereas the carbanion, which is shown in the right, contains three bond pairs and one lone pair. Overall, you have four pairs corresponding to a tetrahedral arrangement. Leaving the lone pair, you will find three bond pairs directed towards the three corners of a pyramid. Now, look at the compound before the fission. Look at the carbon. Around the carbon atom, you find four bonds. That means four bond pairs of electrons. That means there are 8 electrons, and that is what you call as octet, and that corresponds to a stable arrangement. After the heterolytic fission, look at the carbocation. It carries a positive charge. There are 3 bonds surrounding the carbon carrying the positive charge. Each bond is composed of 2 electrons, and 3 bonds corresponds to 6 electrons. We call a system of 6 electrons a sextet, and it contains 6 electrons instead of 8 electrons, which corresponds to complete octet. And so this system is electron deficient because it contains 6 electrons instead of 8 electrons. Most organic intermediates are electron deficient. Now look at the carbanion. You find 3 bond pairs and 1 lone pair, and totally 4 pairs of electrons corresponding to 8 electrons, and so it is an octet arrangement. Next we come to the case when the carbon-carbon bond undergoes homolytic fission. That is, the covalent bond between the carbon and the carbon breaks and 1 electron is shifted to each carbon. Here a double-headed arrow is shown, but in fact when there is only 1 electron shift, it should be shown by a half-headed arrow. This is what you call as homolytic fission, and as a result of homolytic fission, we have 1 electron shifted to each carbon, and these odd electron species you call as free radicals, and these are the intermediates in this case. In the case of heterolytic fission, you have a carbocation and carbanion formed. Carbocation and carbanion formed. Whereas in the case of homolytic fission, you have free radicals formed. And look at the carbon having the odd electron. There are 3 bonds surrounding this carbon, and so 3 bond pairs corresponding to 6 electrons and an odd electron, and 6 electrons plus an odd electron. Totally there are 7 electrons instead of 8 electrons, and so this is also electron deficient, as we saw earlier with carbocation and carbanion. Next we come to this compound. The compound shown here is CHCl3, the chloroform. Here you don't find a carbon-carbon bond. Instead of that, you have a carbon surrounded by 4 sigma bonds, 1 hydrogen and 3 chlorine atoms. And whenever you have at least two sigma bonds attached to the same carbon atom, under suitable circumstances, the following type of cleavage takes place. The carbon hydrogen bond cleaves, and the two electrons in the carbon hydrogen bond are shifted towards the carbon atom. So hydrogen leaves as H plus, and carbon will carry the lone pair of electron originating from the covalent bond. Next, the carbon chlorine bond breaks, and the two electrons are shifted towards the chlorine atom, and the Cl atom leaves as Cl minus. So you see the H plus leaving first, Cl minus leaving next, and so HCl is removed, and we find a neutral carbon atom attached to two chlorine atoms by two sigma bonds, and so you find a carbon which has a valency of 2, and the carbon is neutral, and so this is bivalent and neutral. What I have shown here is known as dichlorocarbene. If you have two hydrogen atoms instead of two chlorine atoms, you will find CH2 with a lone pair over the carbon atom. This is what is known as carbene. And when you substitute the two hydrogen atoms in carbene by two chlorine atoms, you will find dichloromethylene carbene, because CH2 is known as methylene. And this is more commonly referred to as dichlorocarbene itself. In addition, you find the HCl molecule which is eliminated. Look at the carbon having a lone pair. You have two bond pairs and one lone pair. You have two bond pairs and one lone pair, and so three pairs of electrons. That means 6 electrons instead of 8 electrons, and so this is also electron deficient. In general, reaction intermediates are electron deficient. Next we come to this compound. Instead of carbon, you find the nitrogen atom here, a trivalent nitrogen atom attached to an alkyl group, attached to bromine atom and hydrogen atom. Nitrogen carries a lone pair, and here the nitrogen atom is attached to at least two sigma bonds to the same nitrogen. Under these circumstances, the nitrogen hydrogen bond breaks and the two electrons are shifted towards the nitrogen atom. Already nitrogen contains a lone pair. Now you have a pair of electrons from the bond, and so you will have two lone pairs. And the nitrogen bromine bond breaks and the two electrons are shifted towards the bromine, and so bromine will leave as Br minus. In essence, hydrogen leaves as H plus without electrons, and Br leaves as Br minus with electrons, and so you will find HBr leaving the system, and you will find only the Rn. Here you find that nitrogen is surrounded by only one covalent bond, so the valency is 1, and so it is monovalent, and it is neutral. You find two nitrogen atom, two lone pairs over the nitrogen atom. Instead of R, if you have hydrogen, you will have NH with two lone pairs over nitrogen atom, and this is what is known as nitrene, which is monovalent and neutral. Instead of the hydrogen, if you have an alkyl group, you have what is known as alkyl nitrene, the other product being HBr. Look at the nitrogen having two lone pairs. You have one bond pair and two lone pairs, totally 3 pairs of electrons. That means it is 6 electrons instead of 8 electrons, and so this is also an electron deficient species. Next we come to this compound. This is nothing but chlorobenzene. This is an aromatic compound. It is an aromatic ring of benzene in which one hydrogen atom is replaced by a chlorine atom. Here, under appropriate circumstances, under appropriate conditions, during aromatic nucleophilic substitution, the hydrogen bond, the carbon hydrogen bond breaks and the electrons are shifted towards the carbon-carbon bond. This is followed by the breaking of carbon-chlorine bond and the electrons are shifted towards the chlorine atom. And so the chlorine atom leaves as Cl minus. The double carbon-carbon double bond becomes a triple bond. This is known as benzyne intermediate. This is an intermediate in aromatic nucleophilic substitution, the third product being HCl. Similarly, this is benzene disonium ion. And here, under appropriate conditions, when the H plus leaving behind the electrons, these two electrons are shifted towards the carbon-carbon double bond. The double bond becomes the triple bond. The Cn2 plus bond breaks, the electrons are shifted towards the N2 plus, and N2 plus leaves as nitrogen gas. You have the benzene intermediate that is formed, and the H plus ion and the nitrogen gas. This benzene intermediate, look at the carbon-carbon triple bond itself alone. The triply bonded carbon is an sp hybridized carbon. The two carbon atoms which are triply bonded are sp hybridized carbon atoms. This is similar to what you have in acetylene. H, C, triple bond C, H. The bond angle is 180 degrees. It should be linear. But here in benzene, if you look at the triply bonded carbon atom attached to the next carbon atom, which is sp2 hybridized, that is doubly bonded, it is not linear. It is not 180 degrees. It is much lesser than 180 degrees. That means there is a lot of strain in this bond, according to the Bayer strain theory. And whenever you have a lot of strain, that is unstable. And that is why benzene is not a stable compound, but it is an intermediate. And whenever you have less stability, it will always try to get converted to more stable compound. Earlier we found the electron deficient intermediates like carbene, nitrene, carbonium ion, free radicals, etc. In the next stage they will get converted to products when the electron deficiency will be removed and we will have a complete octet around the carbon, and that marks the higher stability. In the case of benzene, you have an octet already around the triply bonded carbon atoms because you have 4 bonds. But there is a lot of strain the bond due to bond angle, change in bond angle from 180 to less than 180. And it will get converted to a product where the strain is removed. Next, you find a tertiary amine, alkyl substituted tertiary amine with a nitrogen containing a lone pair. When this loses an electron, when this loses an electron, just see, electron is removed from the nitrogen, from the lone pair over the nitrogen. You have two electrons over the nitrogen. One electron is removed. That means instead of two electrons over nitrogen, you will have only one electron. And because one electron is removed, one negative charge is removed, and it will also, the system will also have a positive charge. Over the nitrogen, you find that instead of two electrons, you have one electron. And because one electron is removed, you have a positive charge. You have a one electron, so it is a free radical. You have a positive charge, so it is an ion. It's a radical as well as ion. Because it is a positive ion, you call this as cation radical, and this is also an intermediate in some of the reactions. Next we find a ketone, a carbonyl group flanked by two alkyl groups. When this system accepts an electron, remember earlier we saw system losing the electron. Now you see the system accepting an electron. The following thing happens: the pi bond, the carbonyl bond, being weak, it breaks, and the electrons are shifted towards oxygen. Two electrons shifted towards oxygen will leave an oxygen having a lone pair of electrons, and which is monovalent, and so oxygen will carry a negative charge. The electron is added to the system. It will remain as an odd electron over carbon atom. So this system contains an odd electron over carbon atom, and so it is a free radical. It has a negative charge over oxygen, and so it is an anion, and so this is an anion radical. So far we have seen quite a few organic reaction intermediates. They include carbonium ion, that is carbocation, carbanion, free radicals with odd electron over carbon. We have found the nitrene intermediate, carbene intermediate, cation radical intermediate, anion radical intermediate, benzene intermediate. Out of this, the carbocation, carbanion, and free radicals is odd electron over carbon are all electron deficient systems. And even the cation radical and anion radical, if you look at the carbon atom, you find only 7 electrons around the carbon atom, and they are also electron deficient in one way. Whereas benzene reaction is less stable due to the strain in bond angle. And so all of them are intermediates, and they will eventually get converted into products. This is only an introductory discussion about reaction intermediates. Thank you.